So in the previous video, I promised you that we would go from performing arithmetic to actually having logic gates that would implement that arithmetic. But we haven't seen the logic gates yet. We've so far just been talking about arithmetic. But here's where we actually go to logic gates. I wanted to remind you that we've seen two cases. We saw figure 1, which is where we don't allow a carry n, and we saw figure 2, where we do allow a carry n. There were 4 combinations for figure 1, and there are 8 combinations for figure 2. We're going to refer to figure 1 without a carry n as a half adder. So we're not doing a full addition because we don't have a carry n, but the full adder, well, that's figure 2. So we have a half adder which sums 2 numbers but no carry n, and we have a full adder which sums 2 numbers plus a carry n. Notice that basically up here we're just adding 2 numbers, down here we're kind of adding 3 numbers because the carry n carries the same amount of weight as the other numbers. So when we think about a half adder, I want you to think doing addition but with no carry n. And so I have a table here that summarizes the same results of figure 1. So 0 plus 0 gives 0, 0, 0 plus 1 gives 0, 1, 1 plus 0 gives 0, 1, and 1 plus 1 gives 1, 0. We've just formalized it a bit by giving variable names a and b to the inputs, and the outputs are the carry out and the sum, most significant bit, least significant bit. And that's shown sort of schematically here in figure 4, where we're beginning to think of this no longer as just an amorphous kind of arithmetic, but rather we're thinking of it in terms of how can we actually build a circuit that would accept inputs a and b and would deliver an output s and an output c out. Well, when I think of digital design, the first thing I think of is Carnot maps. So let's do a Carnot map for each of those 2 variables, and we find out that it doesn't really do very much help. It turns out that we're very fortunate in many, many ways, and we're going to see another example of that today with 2's complement arithmetic. We're very fortunate that many things work out very easily, but arithmetic circuits is not one of them. It turns out that arithmetic circuits are not very simple because we don't see that there's a lot of opportunity for simplification here in these Carnot maps. Turns out that the carry out is just a and b. That's really not too bad. Over here though, for the sum, it's a and not b, or not a and b. The good news is that we can simplify that down to an exclusive OR gate. So the exclusive OR, if you had your money on exclusive OR, this is where it pays off, because this is by far the #1 application of exclusive OR is in arithmetic circuits. Anytime that you have an adder, either a half adder or a full adder, you're definitely going to be working with an exclusive OR of some type. So if we take those two results and we show them in a circuit, this is what we end up with. The half adder circuit is simply an exclusive OR gate and an AND gate. And so if what you want to do is add 2 numbers and you don't have the possibility of a carry n, then a sum and a carry out can be generated just by using exclusive OR and an AND gate. Down here, we're looking at the possibility of 8 combinations for a full adder. And so I won't read them all to you, but you get the idea. You start from 0 plus 0 plus 0 gives 0, 0, down to 1 plus 1 plus 1 gives 1, 1, or a 3. So what we want to do now is we want to have 3 input digital logic functions that can generate 2 outputs, C out and S. So of course that's going to need a schematic that has 3 inputs and 2 outputs. And it's going to need Carnot maps that are no longer just 2 by 2, but now they're going to be 4 by 2. So we end up with Carnot maps that look like this. Now, again, not as much simplification as I might have hoped. C out is going to be A and B, or B and C, or A and C. In other words, we need to have at least 2 of the 3 inputs have to be asserted to 1. Now, it turns out that we can do a little bit of algebra here, and we can, I don't know if this simplifies it, but it will simplify it when taken in the context of the fact that we're doing this calculation over here for the sum. So this is the basic result, C out equals A and B, or B and C, or A and C. That's the basic result, but we can optimize the circuit as a whole if we do A and B, or A exclusive OR B ANDed with C. And you'll see why that's better in just a little bit. Over here, anytime you see this checkerboard pattern, you can expect that we're going to be looking at some sort of exclusive OR, and especially because I just mentioned to you earlier that even a full adder contains an exclusive OR. It actually contains 2. You could do it as a single 3 input exclusive OR, but since we need A exclusive OR B over here, we're actually going to do it like this. We're going to do A exclusive OR B, and then we're going to exclusive OR that with Cn. So it's sort of like you can take two AND gates and make a 3-input AND gate, or you can take two OR gates and make a 3-input OR gate. You can take two 2-input exclusive OR gates and make a 3-input exclusive OR gate. Now, one thing to notice about the 3-input exclusive OR gate is this case right here, that it turns out that what you want is an odd number of inputs to be equal to 1. So here it's 1, and here it's 1, and here it's 1, and here it's 3. So just be aware that the 3-input exclusive OR gate will be asserted on one input being 1 or on all three of them being 1. It will be unasserted if none or if 0 are 1, and it will be unasserted if 2 are 1. So here's the 3 cells where 2 of the 3 inputs contain a 1. That will not be asserted, but if they're all 3 1, then it will be asserted. So here we have the optimized full adder circuit where we have A exclusive OR, B exclusive OR, C to generate the sum. And then because we had already generated A exclusive OR B, it is just slightly simpler to then AND that with Cn and then to OR that result with A and B. So we end up with here sort of an optimized circuit. It's not the circuit that we would have gotten directly from the K-map, but a lot of people have put a lot of time and thought into how to build the best full adder circuit, and I believe that the consensus is that this is the best one that we can find. So, time to do some examples. If you can go and tackle the half adders and full adders example problem, then come back and we'll talk about how to connect these circuits together.